So this would be a weak acid. You buy that? You know it's weak because if it was a strong acid, it'd be a one-way arrow, wouldn't it? Okay. So basically, also, I skipped over reminding you the definition of a weak acid, or excuse me, definition of an acid is one that donates protons, right? So in your homework that's going to be due on Monday, one of the things that you're going to need to do basically is to look on either side of the reaction arrow and look for acid base, acid base. So my hint to you was to basically identify something on both sides of the reaction arrow that looks similar to each other. So I'm going to actually underline the HB and the B minus. So that's why, and it's important that you'll be able to identify. Do you see where this is a proton donor? Proton donor. That makes sense? Because if you look at it, what it's doing, what it's actively doing, okay, it's donating a proton. Remember when I say proton donor, it's the same thing as H plus donor. Okay? So I'm going to put the word acid here. And I think I might have done that the other day. So let's pick on the water molecule. And now the thing that most looks like it is we call that H3O plus, we call that the hydronium cation. And if you look at kind of from left to right what it's doing, okay, doesn't it look like it's accepting a proton? And I don't know why we do proton instead of H plus, but I try to convince you that H plus is a proton, just a cute little bare proton. Okay, so it's a proton acceptor, then we call it a base. Sometimes I write BASS, our daughter plays bass, accidentally. So that's great. Well, there's this thing called conjugate acid-base pairs, and we'll talk about that next week. But you'll do great with it. If we go ahead and now pick on the two-way arrow says also we're going from right back to left again. So let me circle it. Okay, so I'm going to circle two things that look similar to each other, and I'm going to go backwards now. Okay, so do you see the hydronium to the water molecule? Does that look like a proton donor? I think so too. So actually, I could put the word acid over the H3O plus. And last but not least, going from right back to left again, I could identify the same pair, but now I'm going this way, okay? And doesn't that B minus look like a proton acceptor? Yeah, that makes it a base, officially. And the other thing, remember, we talked about on Wednesday is this idea of chemical equilibria like this. We can write equilibrium constant expressions. And there are equilibrium constants for these weak acids, ionizing or dissociating. We call those Kas, Ka for weak acid. Then we talked about this, where we can actually have a weak base. To me, I think of it like attacking the water molecule and hydrolyzing it, basically breaking one of those oxygen-hydrogen bonds, and then that H plus goes with your weak base, and you end up with a hydroxide ion. Okay. And we could do the whole going back and forth, looking for the proton donor, looking for the proton acceptor, and find acid base on either side. And then this is just a slide to kind of remind you some terms. If an acid only donates one H plus, remember an H plus is a proton, we call it monoprotic. If it can kick off more than one, polyprotic. If it can be either an acid or a base, it's amphiprotic. And I think we left with this slide, right? Water is the most common. It can go either way. So to kind of remind you, well, in the first case, water is being, what, a proton acceptor? Does that look right? Proton acceptor. So in this case, it's being a base. In the other case, water is being a proton donor. So it's being an acid. So I'm going to write base under here and acid under here. So kind of get in the habit of looking on either side. And do you see where your HB is being the proton donor? So that's, of course, an acid. And here your B minus, if you compare it to the other side, HB, it's being a proton acceptor. So that's actually acting as your base. So that's kind of how that goes. So there's, because of, we're focusing on aqueous solutions. And in water chemistry, the strongest acid that can exist actually is the hydronium cation. And the strongest base that can exist is the hydroxide ion. It's known as the leveling effect. So let's take a look at these, and we'll call it a day. Here we go. So for this one, so according to the Bronsted-Lowry theory, label each of these as an acid or a base. So acid is a proton donor, base is a proton acceptor, so A through E. So my hint was this, and I actually kind of did maybe the first one for you. So you have two choices. If you have HNO2 and someone said, is that an acid or is that a base? Is that going to be a proton donor, and so this is what it looks like? Or is that going to be a proton acceptor? So it goes from HNO2 add a proton. It would be, instead of one H, it'll be two H's, NO2 with a +1 charge. I'm going to ask you, I don't ask for much interaction, but let's ask for interaction. If we call this scenario A and this scenario B, how many people think that scenario A looks more likely? Me too. And you could confirm that. There's a whole bunch of tables for weak acids. So you're telling me you think it's more likely to be a weak acid. I think so too. But there is a table that will have HNO2 and it will show this ionization. There'll be a Ka for that. Okay? So if you pick on E, look at E. CH3NH3 plus. So, I mean, does it, to me, looks like it's ready, it wants to kick off an H plus. Does that seem right to you? Otherwise, it's going to take in another H plus. If it's going to be, if this one is going to act like a base, this one right here is going to act like a base, it's going to bring in another hydrogen, and it's going to be CH3NH4 plus 2. Does that make sense? I don't think you're going to find that on the table. Look at C, though. NH2 negative. It's looking like it might bring in a, more like bring in one proton acceptor. If it's a proton acceptor, it's acting like a base. So that's kind of those. The next one is here. Again, multiple parts. For each of these, identify. It's kind of what we were doing today. Basically, look on either side of the equilibrium area and find a pair and a pair. I've done the first one for you. So the HOBR most looks like OBR, doesn't it? Okay. So, but from the left, it's acting as a proton donor. So that would be what, an acid, right? The H2O on the reactant side is acting as a proton acceptor on the product. You know, between, if you compare the reactant to product, it's accepting an H plus, so it's a base. And then we can do, going backwards, doing the same thing. Okay, so it's kind of similar to what we've been doing. So those are your hints for that one. They're just so pretty. They're just so gorgeous. Chemical equilibrium. So I'll push this out there, and you'll have access to it on your Twitter. And